in your brains just even sitting here. And you don't realize how much you are filtering right now, all the things that are happening around you. And you have to get to a point where your brain just can't process and think of everything all at the same time. So you narrow down these things. And at the same time, you're running your body. You're doing all kinds of activities. And if any of you saw the Olympics over the last 2 weeks, for me, it is so incredible to watch these athletes. And they've got 82 billion neurons that are firing flawlessly in order for them to achieve, an athletic level that I know I could never hope to achieve, except for curling. I might be able to pull off curling. But just to understand that the brain is doing amazing things. And I find this organ, most recently, the most important thing I could have ever studied. And it's taken a journey to get there. And this talk is going to be about that journey, as well as where we hope to turn our research towards in the next within the next few months. So the first question, how are mammalian brains built? And it turns out that going from a Neanderthal to modern man, it really hasn't changed a whole lot in 50,000 years, except for the fact that our brains actually have gotten smaller relative to a Neanderthal. And that had to do, they think, with the amount of sensory processing when you lived out in the wild. But here's the other big question, and this is one that we're trying to tackle right now, and that's how do you keep this brain healthy? The fortunate thing is that even 50,000 years ago, there were so many protections that were already set up. We have a skull that protects this organ for us. No other organ in your body has this bony kind of helmet, a bony protection to keep it safe. And that in itself is remarkable. You have the meninges, which are sort of a tough, fibrous series of layers that are protecting the brain. And then on top of that, you have cerebrospinal fluid, and it provides almost a pillow that your brain is floating in. And how many of you have even touched a real brain of any kind of animal? Yeah, all my friends in the front row. But it's one of the toughest kinds of tissues to deal with because it's almost gelatinous. So here's a human brain. I just got this today, so you have to see it because I brought it. It's in eight pieces, but this is a human brain, and I could never lift it up if it were, basically a real organ coming right out of the skull because it's so gelatinous, it just falls apart. And it's very hard to dissect out. It's very hard tissue to work with. So early brain research and how we tackle these kinds of problems. Da Vinci started it in the 1400s and just basically taking brains out of organisms and dissecting it out, taking a look at how it's constructed. This is me last summer with a narwhal brain. So you can get an idea of the difference between a whale brain and a human brain right there. And we're still at that level of just trying to figure out for different kinds of species how their brains are constructed. The thing that's been exciting in just the last few decades is that we now have all this scanning technology. So we can do functional MRI. That means we can take a person, have them in these kinds of scanners or magnets, and have people do things, think about things, or lift their arm, do all kinds of motion, and we can start to get an idea of oxygen consumption and metabolism going on in different parts of the brain, blood flow going on in the brain. Excuse me. Here's a CAT scan. This is a lion. That an African lion that somebody decided this animal needed to have a scan, and so they tied this animal down. He's sedated, it's alive, and they were doing some veterinary work with him. But you look at a picture like that, and then you look at this and you go, do we really know anything about the brain real function? I mean, think about it. We're out there doing amazing athletic things. We're out there running around. You're at altitude, you're diving, you're doing all these things. And this is how we've had to look at brains. Most of our research has really been at the tissue level. You can do it molecular to biochemical, doesn't matter. Or looking at it with the human or animals prone, resting at some level in a scanner. That's where the technology is. And so we've decided, actually I've decided, my lab doesn't even realize what I'm doing here, to take a journey with the brain. And we call it the Untamed Brain Project. And what we're trying to do is say, how does the brain operate in the real world, and how well is the brain protected in the real world? So what I'm going to start with is I'll give you a little bit of science, what we know so far, what got me to get to studying the brain, some personal experiences that caused me to really want to do this, not the least of which was a concussion that I had, but I'm not going to talk about that, but it did factor into this. Some hypotheses that I've come up with, and then what the future neural adventures are going to be, and then a cat's plan for your own brain health. So if you hang in here to the end, I'll give you a few ideas on how to keep your own brain healthy. So we start with the Neanderthal, and this is Mike Gerhardt. He's an extreme surfer, and we started with some technology that we had developed in my lab, and it was new instrumentation for exercise monitoring in field conditions. So instead of having somebody on a treadmill, we were going to monitor how the heart responded to big wave surfing with Mike Gerhardt out at Mavericks. So we had this monitor, added just some neoprene over it. He was going to have his wetsuit over that. And then, of course, some duct tape, because you have to have duct tape when you do these kinds of things. We started at the bottom with these and got him geared up and then sent him out into this. Any of you that have ever seen the big wave surfing off our coast, it is frightening. And I felt so horrible actually sending him out, because in the end, he was there for 4 hours wearing this thing, and the pressure of those waves coming over these surfers actually pushed the unit that was on his chest into his sternum, and he had a massive hematoma on his, I know, who knew? But I didn't know about, the physical forces that he was experiencing. And here's what his heart did. Even, so the parts right here where it's tan, that's where he's on the beach. Even before he got out into the water, his heart rate was 180 beats per minute. When he got on the waves and was actually surfing, that's those 4 triangles where he's on top of the wave, heart rate was 200 beats per minute. And he held this for more or less 4 hours while he was surfing. He was exhausted after it. Pardon?
What is his resting heart rate?
50. So he was a little bit excited. So, and here's what we found. Without giving you a lot of details, there was an absolute cognitive overdrive in these extreme sports. These people are amped up out of their minds when they're doing this. This is the stress response for him being on tall waves. And then this is really the amount of exercise he was doing. And then this is what the surfing did for him on top of it. So it's as if the heart and the brain have been almost disconnected, and we're in brain overdrive, dictating what the heart's going to do, as opposed to just a simple exercise response. We took them on short waves, and I can tell you these big wave surfers are always amped out of their minds, and they have really high heart rates, even on short waves. And then if you're a novice, you tend to have a much lower heart rate. The bottom line is that there's this cognitive overdrive. You have probably experienced this yourself, because when we looked at bowlers, this is probably like curling, even when you're standing there and you haven't done a whole lot of exercise, their heart rates were about 80 beats per minute. But this 120, this was when the person was standing, the ball is already released, and they're just hoping it hits a pin. That's all it was. So again, there's this overdrive about what's happening with your heart that's directly connected to the brain. all of this got the attention of the Office of Naval Research, who was having to deal with some really big problems about oceanic noise. They said, can you take your technology and help us to understand what is happening when we are putting sonar into the oceans, and the fact that there are strandings that are happening, particularly with beaked whales, these really deep diving whales. They said, can you do something out in the wild for us? And this is what they were facing. You know, a Navy exercise would go on, and then there would be cetaceans that would come up on the shoreline within a day or so, and the question was it truly because they had put noise into the ocean, or was it something else? One of the things I can tell you, when these kinds of events happen, they'll go in, they'll necropsy animals, they'll look at all the organs, but the one that they tend not to do is the brain, because getting into that skull is so hard. Nobody wants to deal with it, so there's not a lot of information about what's happening to these animals in their brains. I'll show you a little bit, but it's a huge problem. You know, trying to figure out why these animals died, and did the noise do it? So in this table, don't worry about the details. The only reason I show this is because there was a report put out by the Navy, and it said, at least for these 5 events, definitely we were in the area. Probably the noise caused a problem, and here are all the kinds of things that were happening in terms of the pathology. So don't worry about it, other than a whole bunch of organs seem to be involved with the problem. When the reports came out, though, they went for the big sample sizes, and they went for the tissues that they could basically report on. And so they reported on cardiac and skeletal muscle damage. It seemed as though there were problems there. There was fluid and debris in the lungs. You can imagine if an animal, if something happens to it, it's going to drown. You know, you're going to see these things. And suddenly, the Benz hypothesis was born. People were saying, well, we're seeing some gas emboli, some fat emboli. Marine mammals are getting the Benz. And this was heresy in the marine mammal world, because basically, marine mammals aren't supposed to get the Benz. They're supposed to be really safeguarded from this. And I will admit up front that I was really skeptical, because it seemed as though there had been, you know, thousands and thousands of years of evolution, of adaptation, that would prevent this kind of thing happening. So I couldn't get my brain around the fact that somehow noise was connected to these animals getting the Benz. And that's where we started looking into it a little deeper. So how many of you have heard about these whale strandings? And people are there and they're trying to push the whales back into the water, and they go, we don't understand. They're confused, disoriented. Seems as though their navigation is off. They just keep coming back and beaching. Why is that? And so that was sort of clue number 1 for me. Maybe there's a cognitive problem here. There's something going on with the brain. The other was that when I started looking at these reports, and the number of times you see hemorrhage of the brain, head and lymph node congestion, hemorrhage in multiple tissues, including the brain, over and over and over again, it was showing up. And at least for the animals that they looked at in detail, something had gone wrong with the brain, and probably associated with the vascular system and the brain. You know, and so that's where we decided to take a look at that organ. You know, while everyone was chasing the Benz, we decided to try and do the brain. Hang on. So, are all brains the same? So how many of you think there's a terrestrial mammal here and there's a marine mammal here? How many of you think that the light-colored brain is the marine mammal? Oh, this is a really smart crowd. And then, how many of you think it's the dark brain? And that's the answer. So this is a coyote, and this is a sea lion. And I don't even need to know where the brain came from. If you show me the color of a brain or a picture of a brain, I can tell you if it's a marine mammal or a terrestrial animal, because over and over and over again, whether it's mountain lion or coyotes or sea lions or dolphins or whales, the brains of marine mammals have a lot of vasculature going on. They have a lot of neuroglobin, so globins that help to hold on to oxygen, just like hemoglobin, just like myoglobin. They have very different brains biochemically, and so when you see this kind of a brain that has this much vasculature on it, imagine having 2 to 3 times that vasculature in order to feed the brains of these marine mammals. So structurally, very, very different, and even biochemically very different. You don't need to know the details here other than the fact that the deeper the animal goes, the more it's going to rely on blood delivery to the brain to provide the oxygen. And that's different for some of the shallow animals, more shallow diving animals. Fast swimming animals, they tend to rely more on these globin proteins in there. So of all the animals that we're looking at, the deep divers have brains that are more vulnerable to a hypoxic hit if something happens to the vasculature, something happens to how the heart is going. So here's a challenge. This is my, I always want to say Mark Spitz. It's Phelps. Same body, same thing, it's all okay. So when you compare a human swimmer versus a dolphin or a whale or a seal, how do you hold your breath and exercise at the same time? We got a big problem for marine mammals. We swim on the water surface, so there's always oxygen available to us. But imagine you are exercising as hard as you can, and you're doing that all in a breath hold. That's what marine mammals are trying to do. So if I took this entire group right here and I said, okay, take a big breath, don't do it, because then we're going to have to listen to you exhale. But if you took a big breath, held it, and I started taking blood samples out of your arm, and I looked at how much oxygen was in your blood. So this is the PO2 of your blood over there. This is your breath hold duration. You've taken a big breath, and what happens is you start with maybe maximally 100 millimeters of mercury of oxygen in your blood. As you hold your breath, it's going to go down, so we get down to 50. You get down to 30, and you are now in the zone of human shallow water blackout. That's when we go unconscious. Your blood level gets down to that. You are going to be unconscious. Look at marine mammals. This is what they're doing. They're getting down to levels of maybe 10 millimeters of mercury. All of these animals, if they had the same brain as we did, would be unconscious while they are diving. So that's the difference. We've got something very different happening with these marine mammal brains and oxygen than what we're dealing with as humans. And then these 2 arrows, this is for maximum dive duration for Weddell seal, and then the red one is for dolphin. So you can see what's happening here, and they get, as I said, very, very low levels of oxygen in their blood. So this is a challenge of diving for a marine mammal, because there are different responses that are going to control what's happening to the heart, and they're going to be trying to move blood that has really low levels of oxygen in it. So because of the dive response, when these animals put their faces in water, even if I had you put your faces in water, your heart rate's going to go down. You're going to go into a diving bradycardia, heart rate goes down, and it's a way for your body to basically preserve whatever you've got in the way of a scuba tank. However, for a normal exercise response, they should go into tachycardia. Well, I put you on a treadmill, your heart rate's going to go up. They're swimming faster. So what's the heart going to do? Is it going to go up or is it going to go down when the animal is trying to swim underwater? And we came back to our custom-designed EKG unit, put an accelerometer in there so we could monitor the swimming movements of these animals, and put a depth monitor in there. And so we were able to look at diving depth. We were able to look at what the heart was doing, how much blood it could provide for the brain, and then look at how many strokes it took, how hard it was exercising. And we did this with 3 groups of animals. Things don't stick to marine or dolphins very well, and so we had O'Neill make us a little wetsuit, and he's wearing his heart rate monitor. There's a couple little surface electrodes there. And we started with dolphins at Long Marine Lab. The facility is amazing because it allows us to set our baseline. The animals can dive, they can swim really fast. We're now going to understand how the heart is related to stroking and shallow depths. Then we went to Weddell seals in the Antarctic. This is a deep diving, long diving pinniped. And then narwhals in Greenland. An amazing situation where I can get my hands on a very deep diving cetacean. And I don't have a lot of time to do everything, so I'm going to tell you about the narwhal part of it, because you probably haven't seen a narwhal. I mean, why study narwhals? Because they're cool. I mean, it's like, I wish I could say it was just a science, but I got asked to do this, and I was like, yes. But here's the other reason. The other reason is that the animals that are in trouble with noise are the deep divers. And so a lot of the beaked whales are in trouble. There's a beaked whale, Blainesville, on the other end there. And the narwhal dives as deep, as long. It's one of the deepest diving marine mammals out there. And it was an opportunity for us to work with them because of a very unusual situation in Greenland. So we were working off the coast of Greenland on these animals in the fjord lens. This is one of our heart rate monitors. This is actually an old version of it. That's about 4 years old. We have a new one now, smaller. And it's got our EKG and our accelerometer and our depth meter in that. And that's the EKG pattern for a narwhal. And it looks just like yours, only it's a little bigger. And this is the situation. The narwhals come into these fjord lens, and the hunters put up nets. And so they get entangled in the nets, and what we do is basically disentangle the narwhals from the nets, put our heart rate monitor on them, and then send them out. So they're basically being rescued from the nets, sent out. This is work with Mads Peter Hyde Jorgensen, who works for the Danish government, and Susanna Blackwell, who is a techno person with our group. And it works really well, and these animals, like I said, they're coming into very shallow areas, which is unusual for a deep diving cetacean, and provided an amazing opportunity. So I want you to hear the sound of a narwhal heart rate. So that's it breathing. But their heart rate is about 60 beats per minute. It's not all that different than our own heart rates. Gets a little excited there because I'm getting too close with the camera. And that's a immature male, so he's got a little tusk. So we monitored heart rate.
How is it fastened on?
How is it? A suction cup. Yep.
Do you have to retrieve it?
Yes, and I took all those slides out. I didn't have enough time. We put them on with suction cups. They stay on for anywhere from 16 hours to 4 days, just depends on the animal. It falls off, it has a radio tag and a satellite tag, and then we have to go out in a boat and try and find, in amongst all the icebergs, our tag. So,
We catch the narwhal.
no, the narwhal, once we've tagged it, it's off and running. It has a different satellite tag on it that stays on it, and it's used for monitoring long-term movements. But for us, the instrumentation's for about 4 days. But here's what happens. This is a thing that was so crazy, and I didn't expect it at all. 60 beats per minute is our start. Animal goes on a dive, goes through the bradycardia. Now you got to understand, this is an animal that's trying to swim as fast as it can because it's just been captured in a net. It's on a series of escape dives. It wants nothing more than to get away from us. And here's what happens. Goes on the first dive, it doesn't know what's going on, goes into an extreme bradycardia here, comes up, takes a breath. Look at this. The animal gets down, it's underwater, and its heart rate is 3 to 4 beats per minute. It was unbelievable. And in time, over the course of an hour and a half, it starts to look like a normal series of dives, and then it goes on. But those first escape dives are something that we had never seen before and is so extreme. So remember the heart rate that I just played for you before. This is it on a dive. So that was 1. Got to wait for it. It's coming. It's like the longest 20 seconds. There's the second one. So that gives you an idea of 3 to 4 beats per minute. That's a long time. Your heart has beat, 5 times to 20 times in that period of time. And this animal has to get blood from that heart to its brain. And here's the other thing that happens. When you get these extreme kinds of bradycardia, here's the normal one where you've got beat, beat, beat. Everything's looking good. But in the middle, you start seeing things like beat, 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 beat. You get these irregular rhythms, and we get premature beats. We get all kinds of anomalies happening when you've got this extreme situation occurring. What could go wrong? I'm going to show you a piece of video here, and it's a cartoon representation because it's built from the actual instrumentation. So remember, we had a stroke meter on the animal. So each one of these little red triangles is when the tail beats up. The other part, this track right here, is the path that the animal is taking through the water. And then I want you to see what it does as it goes through this dive. So the little cartoon narwhal is swimming. There's a great big tail beat. Here's one, here's one. It should really be more rhythmic, and it's doing some pretty crazy beats here. It's at about 30 meters right now. Great big beat, and then watch this. It goes into, the only thing we can figure out is a seizure, and it's dead. At that point, the animal's pointed up, and this track just goes down, and it drifts down to the bottom of the ocean, and it's gone. The only reason we know that this happened is because we had the instrumentation on it, and the suction cups pop off. We got the instrument back, and this is what we recorded. And you're going, what causes an animal to have a seizure like this and to die? It was gone. We never saw it again. So here's what we think is happening. In these escape responses, this is the three things that the animals have to put together. An exercise response, it's trying to swim as fast as it can. It's got a dive response because it's underwater. And then the third thing, the fear response. And when you put those three things together, look at what the heart is getting. It's getting a signal saying beat faster because of exercise, beat lower because of diving, and then beat really, really low because you're afraid. And that combination of fear, diving, and exercise is lethal. It's lethal for mice and rats in a laboratory. It was lethal, they think, for the vaquita when they just did those captures. Remember, there was this problem where they tried to capture the last vaquita, bring them in, had cardiac myopathy. And so they think that this is what happened. We think this is what happened for our narwhal. And it results in a massive hypoxic challenge for the brains of these animals. So these animals are not built for doing this kind of response. Neither are humans, because it turns out, like an idiot, I did a race like this. And so this is an Ironman race up in Oregon. And when you are standing there at the start of a triathlon and you've got all these people, you are amped crazy out of your mind. You could not have more fear going on. Your heart is pounding. Then you tear into the water because the cannon goes off, so everybody, 1,000+ people, are going to jump in the water. You're terrified, and there are people that didn't make it. There was a person that died on this race. They were always attributed it to drowning, and it wasn't. It was a cardiac arrest, and it was because you had amped up crazy fear on top of trying to swim as fast as you could, and a cold face submersion, which causes a dive reflex, and that combination was a killer. However, because of that, and because friends of mine also work with the U.S. Triathlon Association, and because we told them about this, they now have this kind of a start for triathlons because they can cut down on the fear response, have people go out on the race. They're a lot calmer, and as a result, they haven't had a fatality since. But there's been several races before this, one in New York, and as I said, Coeur d'Alene and a couple other places where this had happened, and always attributed to a bump or something, but ultimately it was cardiac arrest. Okay, I'm going to give you my stroke of genius here. This, so there's a personal side to all this. I've just given you a whole bunch of science, but February 10th, 2017, we've got this big stranding event in New Zealand. We've got 240 whales on top of 416 pilot whales have come up. 2 days later, my husband has a stroke. So in the middle of me thinking about brains and what's going on, I walk into an MRI that looks like that, and I'm going, oh my gosh, the brain is a delicate thing. And here's what I learned about stroke in that moment. First is the patient doesn't know they're having a stroke. I didn't know that, but they truly don't know what's going on. The damage occurs within seconds. You don't have long to get the patient in. Reperfusion, variable blood flow, can be as damaging as the original stroke. Brain repair overstimulates the neurons, and the patients are confused and disoriented. So you can imagine, as I learned about this, who's confused and disoriented on a stranding? Who's got blood that's come into the brain after being potentially exposed to noise? These animals that have stranded. And so we started looking for what was happening, and this is what I find just amazing right now. There is a pretty common mechanism. The actual details may be slightly different, but there's a common mechanism for dealing with injuries within your brain. So remember in the beginning we had all these sort of neurons that were talking to each other. We start with our presynaptic, our postsynaptic. You have a bunch of glutamate. That's just the transmitter that's allowing your neurons to talk to each other. This is normal. This is what happens with stroke and ischemia. Glutamate all over the place, you can't get rid of it, you end up with all kinds of nitrous oxide, and just realize you've got big problems. But the interesting thing is stroke, ischemia, Alzheimer's disease, seizures, Parkinson's, Huntington's, and concussion, same basic mechanism. It's an excitotoxicity that is occurring here. And with concussion, here's this famous tau protein that people talk about with football players. And just 2 weeks ago, I think it was in PLOS 1, woodpeckers. Who knew? You know, here's an animal banging its head against a tree its entire life, and it's now showing this tau protein. So even though there are animals that are doing these kinds of things in the wild, they're not getting away scot-free. Here's the really other peculiar serendipitous thing that happened. So while I'm sitting in the doctor's office waiting for Jim to come out, I get an old National Geographic that's sitting there. It's from 2011, and you're like, oh my gosh, here's a 2-page article on hits that a football player has had. So they put accelerometers in a helmet and said, how many times was the head hit by a football player? And these are all the hits that had occurred, and it was 527 hits in one season. But here's the thing that amazed me. Concussive brain injury is not just about the magnitude of the hit. It wasn't always the biggest hit that actually caused a concussion. It's the number of hits over time. And that's where I started to piece all of these things together, because the brain is not meant to be shaken. Remember I said you've got this gelatinous thing right here covered with a bunch of capillaries in a hard shell. So you shake it, you hit it, and you're going to have problems. You're potentially going to have bleeding as a result of capillaries being bursting, and that's what this is showing here. Who's got all the big capillaries covering their brains? Deep diving marine mammals. So now the question is, could it be sound? So here's my wild speculation. This is a pure hypothesis. But could naval sonar, seismic pulses that are used for oil exploration, act like a punch, not just one punch, but over and over and over again to the head and the bodies of marine mammals? So I want to play you just a seismic sound so you get a sense of just these pulses. And this is an old sonar signal. But imagine explosions happening like this, and the way that oil exploration happens is you send out an explosive pulse, and then you wait for the reverberation, and then you send it out again and again and again. So it was not lost on me that that New Zealand mass stranding event happened in the spot that I have right there. And people were saying, well, it was a hook and the animals just happened to lose their way. But in that week, the Amazon Explorer, the world's biggest oil survey ship, was in that area for the first time. It's all circumstantial, I will admit it, but it also seems suspicious to me that you've got giant pulses happening in the water and a major, major marine mammal stranding right next to it. So this is what our research is going to do, and I'm sort of winding up right now, and that's how much sound vibration can the mammalian brain take before you get injury? On the one end, ultrasonic. The way that we do our biochemistry is we liquefy the brain using sounds. Ultrasound will cause the brain to liquefy. On the other end, you've got minor brain damage from a woodpecker, just sort of pecking for things. But here's what we know. We know that gunshots and we know that explosions cause shell shock injuries. There's a whole host of information from the military on this. But they're starting to realize that this shell shock situation can be just from the pulse of the shooting gun. You don't have to be shot to have damage to your brain and to have some of the symptoms that we've seen for football players and for boxers. All of these things are connected. They're all impulsive hits to the brain. It's just that some are through sound and some are through a physical hit. You know, it's funny, and I don't want to get political, but this is like the one reason you would not hand a machine gun to a child with a developing brain. That kind of concussive sound, I think, is a problem, a huge problem for anyone. It's a problem for adults. You can imagine with a developing brain. For whales and sonar and seismic, in terms of a traumatic brain injury, we don't know. But this is what we're going to be exploring. And the way we're going to do it is we're going to start working with functional near-red spectroscopy coupled with our EKG monitor, and start to put instrumentation on the brain that for the first time will tell us about heart rate control of cerebral blood flow and oxygenation during free-ranging conditions. So now we can get an idea of how the brain is responding, how much blood is getting there, and what happens when you're in different kinds of situations. And I can tell you, I'm going to start with my nephew, who's a who is a heavy metal drummer, and I'm going to look at what happens to his brain when he is there pounding with you notice there's no earphones or anything on this character, no earplugs. Is this a problem? Are sounds a problem in our environment? And how far can we, go with this? Are earbuds a problem? Are people that cram microphones into your ear and blast sounds into your brain, is that a good thing? Maybe it's not a problem at all, but to me, it's something that's worth looking at, and that's what we're going to do with this new kind of thing. So, last part. How do you protect your brain? So just think cats. Stay away from concussive activities is all I can tell you. And I mean excessive sounds. When I go to the movies now, I wear earplugs. I just do. It's too loud for me. If it's thumping in your chest, you can guarantee it's thumping in your brain. Extreme sports, totally up to you if you want to do it, but just be aware that multiple hits over and over and over again are going to be problematic over time. When I say time, turn down, turn off. I don't care if you do yoga. I don't care if you go outside, but just try to stop that overstimulation that's driving us all crazy. For training, I tell people try to do a little bit of interval training when you exercise. Don't just do just sort of the low, slow, you need to have healthy capillaries. And the way that you build healthy capillaries in your brain is give yourself just a little bit of a challenge. A little bit of interval training will help you. And then stimulate your right and left brain. Because, go from art to science. And to me, I physically feel different when I'm doing science, when I'm doing art type projects, and when I'm doing math. It's just different parts of your brain. So with that, I'll say if you want to join us on our scientific journey of untamed brains, we are just getting started with this. We're really excited, and I'm really glad to tell you about it. So thank you for listening. Questions? Oh, there's one. Oh, am I allowed? Wait a second. I think they have microphones. Yeah.
Thank you very much. This was outstanding. Professor Williams, so I don't know if you heard in the news, but there was some strange event, apparently at the Cuban embassy or Cuban...
Oh, yeah, the sounds.
That apparently had to do with sound, and some number of months later now, apparently the people are experiencing various other physiological things. Have you been following that?
I have, and I don't know what the sounds were. I'll tell you one thing that I didn't put into this talk just because it was just too much. But it's the whole cognitive, behavioral side that is associated with this. So when I started talking about injury to the brains, when there's a hit to the brain, and I know this, for myself, and I know it, for my husband, and then as I got into the literature, you become very anxious. And when they're divers in the water, when they heard some of these sonar pulses, it was the same thing. And I believe that sort of toxicity that happens with all that glutamate, when that is released and you've got the repair process going on and you have injury that has happened, there are cognitive things that I think are happening. And one of the first ones that I'm saying is this feeling of anxiety, and then it can spin out from there. So I have no doubt that there can be sounds, and it's going to just drive you crazy in a way. But it creates the mood swings. It's, you hear it with post-traumatic stress syndrome, with in the military. And as I said, as they get into this, it's not just because you're in a terrible place and you've seen terrible things. If you couple that with an injury, you can see how you would end up in that kind of a situation. Yeah, and so that's a whole nother part of what we're exploring. So, good question. Who?
I'm next.
Yeah, sorry.
Thanks for the talk.
Thanks.
What percentage of the narwhals died after they were released?
We don't know.
The ones you tagged.
For the ones that we tagged, we've only had 3 that died. So there were 2 events that we saw with this kind of a seizure that we're just now trying to figure out. One was shot. It was a hunter ended up shooting it. So it's not every animal. But here's the thing that we learned from doing these studies, that we didn't want to be a part of the problem with the animal either. And so what we did was go in and do a really fast release, as fast as we could. So it became a game of radio signal or radio information between us and where the hunters were, and they'd say there's a narwhal. We would scream out there, suction cup these things on, and it was gone in 9 minutes. And we never had a problem with an animal like that. The ones that got caught in the nets and were in there for upwards of an hour, and you get beyond that, that's where I think we start to see the problem, and then it becomes this extreme response. So time is a factor, and I think it's just stress level that the animals are experiencing or causing some of these things. So yeah. People want to go home. Yeah.
I actually have 2 questions. The first one is, the deep diving narwhals, they get more impacted when they have these very powerful sonars. Is it because, the echo waves from the bottom, they hit them harder because they were deeper? That's the first questions. The second question is a little bit quite different. The picture you show between the human skull and the Neanderthal skull looks like the Neanderthal skull is all in one piece, whereas for human, when you're young, it comes in several
Sure,
pieces.
yeah.
So, from an evolutionary perspective, what happened?
Do we have an eggshell that's developed? I mean, you can see how robust it is for the Neanderthal skull, and so yeah, I mean it's become thinner over time. In terms of the sutures, I don't know. You're a morphologist. Do you know more about sutures and brains of ancient versus modern man?
No, I mean, we know that it varies across mammals.
Yeah.
Musteloids, they
Wait, here's a mustelid man that's looked at a bunch of skulls.
Little kid Neanderthals would also have sutures. So you just saw it in an adult, that's why it's super fused, but if you saw a juvenile Neanderthal, it would also be in pieces.
Yeah, so who knows? Yeah, I don't have the details on that. In terms of your question about the reverberating sound, that's a really, really good one. And we are just now getting to the point of saying sound physically is a problem. And we hadn't even thought about it before. And so it is the reverberation, it's the multiple hits that are going on at the same time. And it's going to be very different if the animal is in that near field sound versus far field. And we just don't know. That's basically what we're going to try and explore is the variation in sound, and not just the sound, but the pulse that's created. And it's a little bit tough because everything's in decibels. I mean, everyone says, oh, it's loud or it's soft. But what we're talking about is how frequently a pulse is coming towards an animal, and how does that change the acceleration of the head? And specifically, and I don't know that we'll ever be able to get this, it's the acceleration of the brain within the head that we're trying to figure out. So it's all new science. I'll come back
Thank
in
you.
10 years.
What's your research and what additional support do you need to carry forward with your
$100 million.
work?
So normally the people that supported the original research was Office of Naval Research because they wanted to know what was happening. Oil companies are not happy with me right now, so I'm not going to see anything from them. It's pretty, I mean, you know about the war on science, and we're starting at zero right now. And what we're doing is the NARWHAL work is supported by the Danish government, so they support all the logistics and that kind of thing. ONR helped me to build the EKG units, and then when it comes to the units for the brain, those are probably going to be 20,000 a shot, and yeah, we'll put our hand out. I think eventually it's going to have to come from foundations. I don't see that this is so novel and so potentially inflammatory. I mean, think about it. I can get oil companies mad at me, sports groups mad at me, gun manufacturers mad at me. It's amazing.
If they have enemies too, I'm going to be willing to support this type of research.
Who? The military?
No, I'm just talking about people that might find this useful for their own commercial purposes.
Like Greenpeace or something.
Yeah, you know, we've never been very lucky, and with a lot of the animal organizations, and part of it is because, you know, we're doing biology, we're doing, you know, and so we've got our hands on the animals, and these are not behavioral kinds of studies, and that tends to be what gets supported by them. Nothing wrong with that, it's just that when you're saying, I want to put instruments on animals, some people find that an invasion of privacy. You know, it's just the nature of it. So we'll see, you know, NSF has no money, NIH is like, oh, you're studying animals, we don't care, you know, it's only humans. So we're in that fine, horrible line. We're going to do it anyway. I'm going to figure out a way. I mean, it's just too exciting, so. So he's got a microphone, do you have a microphone?
Not yet.
Okay.
Yeah, so you mentioned wearing earplugs would help. Is that, you're thinking the sounds are getting more in through your ears, or you think it would be everywhere?
You know, the issue is really, as I said, the brain moving relative to the skull. That's, you know, it's basically taking this jello and smacking it on the inside of your skull. And so a lot of the work that I've seen has been, you know, I'm trying to decide whether I want to get morbid or not. The earplugs are simply protecting your ears. And so when I say earplugs, that's, you know, it'll protect the hair cells in there and maybe you won't go deaf. It's not going to protect, you know, that physical moving of your head. And like I said, when your chest is moving, and I've been to concerts like this, I went to an Adele concert here. That should have been easy. And oh my gosh, it was so loud. It was painful in my lungs. And you're going, what is, you know, I felt physically sick by the time I was done. It was too bad. It was a good concert. So it's that kind of shaking. And the reason I sort of harp on it is that when you start looking at military, you start looking at policemen, a lot of people that are shooting guns and not necessarily being hit, that these are the people that are starting to show these tau proteins and damage. And, you know, you start to realize that it isn't necessarily getting blown up. It's just being in an area where there's an impulsive force that's come by and hit you in the head. So we're just saying, let's recognize that. In terms of the earbuds, the only reason I sort of harp on that is that you see these kids, and my nephew's half deaf, going, what? And you wonder, I just wonder physically what's happening there. So again, that's me wondering. It may have no impact at all, but we'll take a look. So yeah.
So I was actually going to ask a very similar question, excuse me, about whether you believe that is if the damage to the animal's brain is actually from the concussive force of the acoustic wave hitting the skull versus coming in through the ear canal, through the eardrum, et cetera.
Yeah.
Because that's, I mean, to me, it's, you know, that's an obvious entry path, because the sounds are normally coming in there. It's obviously there's no you know, the skull, as you said, is pretty hard.
Well,
there's no reinforcement in the ear canal. So, I mean, is it a combination of both, or do you feel that it is really one or the other, or?
It's probably a combination. But having said that, I will say that there was one of the most bizarre studies that I had ever seen, and who knew, you know, it's buried in there in the literature, and it was a review that was done by the military, and they were trying to figure out if somebody were to get shot in the body, would you have a brain injury because of the concussive force of being shot? And so this would reverberate, and there's all kinds of theories about, well, it's coming through air spaces, and so the lungs are reverberating and it goes up to the head. Some people think it's the circulatory system, and so you've got a pulse that's going up through the conduit, through arteries and veins and such. So this was a study that somebody said, well, let's look at animals that have essentially been shot at with a big explosive grenade. And they went up and went on a minke whale hunt. It was a whaling hunt. And so the harpoons that they use to kill these animals have a grenade on the end of them. And they are shot in different parts of their body. And so what they did was they brought up the carcasses of the whale and they looked at where did the grenade come in, what got destroyed, and what did the brain look like relative to that. And it was amazing, because if the grenade was near the head, pulverized in terms of the brain. And as you went further and further back, you had all of this injury from broken blood vessels. And so the actual thing that killed the animal in some of the cases was not that they had gotten shot in some muscle mass, it's that the brain did exactly what I said. It busted the blood vessels, and the animals essentially died from traumatic brain injury. So, so I think it can happen anywhere along the body, and there are conduits all through. And maybe you're right. Maybe the ear canal is just a good one.
Have you done or thought about doing experiments using acoustic waves in a lab setting underwater, where you have either, you know, I don't, some kind of you know, animal that you could maybe I don't know, dead animals or substances that would mimic the brain tissues, to actually, you know, in a controlled laboratory environment, see at certain levels of acoustic waves what kind of energy is imparted into some kind of a tissue through
the skull.
To actually, you know, measure those things?
Yes, I have thought of these things. You know, I stay up nights going, I wonder how I can prove all this. But actually that's a good thought. What I thought was doing just that. What if we took a carcass? It won't tell us about bleeders and that kind of thing, but it'll at least tell me, you know, what the brain tissue is going to do. And we could measure the acceleration on the outside and on the inside of the skull. And then have this carcass, whatever it is, a seal or a dolphin, you know, some dead thing that's come up on the beach, and then have its head out of the water, and then have its head in the water, and see, you know, how that changes. So I think that's the way that we're going to have to go. We're never going to do this on live animals. You're just not. And so as a result, that's going to be a starting place, and then starting with different kinds of sounds for people that have exposed themselves, like my nephew, the drummer, to get an idea of just really what's a lot and what's a little. What I haven't completely figured out, though, is the exact test. I'm hoping this NIRS, this near infrared spectroscopy, might be able to give us a metric that says the brain is going in this direction and the skull's going in that direction. So using that plus the accelerometry is the testing that we're going to try and do. So like I said, it's all new. I'll take any idea at this point. They're doing microphones, but they're...
When you did this, go through this Australia, I think, Newfoundland, Australia, whatever, Arctic.
Oh, the
Antarctic
narwhals.
thing, right.
Yeah.
Is it the same species that get beached out that get affected, or is it all species get impacted?
This is a good question. This is a very political question.
No. Why I'm asking is,
No.
Is there some kind of a harmonics that affect some species, and some harmonics, the echoes they use?
Yep. So it depends on where you're looking in terms of where they're doing the oil exploration or where they're playing back sonar. So the only thing that they know is from all of these events where you get these mass stranding events, and they're an unexplained mass stranding, that people then say, was there any kind of sound? Was it a seismic exploration going on? Was there sonar going on? To get people to admit that they're going to be in an area is tough, so trying to match the bodies with events that are happening out in the water, that little list I had of the naval operations, there are shallow water species in there. There may even be pinnipeds in the area. They did not strand, the deep animals did. So maybe this reverberation from the bottom is a good, maybe that is a mechanism that could be doing it. For the narwhals, the Danish government has been looking at what's going to happen off the coast of Greenland now because of the reduction in ice. They now can open all of these coastlines for oil exploration, and so they're looking at when and where they should do this. So part of the reason, you talked about funding, part of the reason the logistics are there is because they're trying to get a handle on it before it becomes a problem for the narwhals. So they actually last year brought in a seismic ship, parked it outside of the fjord area that we were working, and we did just some of the first behavioral observations last year to see, do the narwhals even see it? I can tell you they hear it and they're like, we're out of here. We're not going to hang it in here. We're going to go back this summer, and I think they're going to do it again. And again, it's to see what are the animals going to do behaviorally, and then if we have our instrumentation on, what kinds of biology are we going to see if that happens. So different species, gray whales don't seem to care about anything. You can
Right.
play anything there, and they're just like, yeah, so what? So it's not every species, and maybe it's these deep diving, mid-sized cetaceans, odontocetes, that seem to be the ones that come up all the time.
Maybe if they change the frequency of the sonar.
Well, and that's it, and you can also do it at different times. So we know where the narwhals are going seasonally, and you can say, do not come, or don't come in this particular fjord, they're just always there. So that's the idea, that if we're going to do this kind of selling of coastlines for oil exploration, that you set up sort of the timing of things. So,
Thank you.
yeah, we'll see.
It's amazing.
So I get one more question, and she's saying who's going to do it.
So I've heard that sperm whales use acoustic blasts, and there's species of shrimp that do. Have you used any of that, those studies, to inform yours?
Yes and no. What we've tried to do is come up with sort of a range of natural sounds that are out there, and the sort of the sound level that's produced by them. The little bit, as I said, the little bit harder thing has been trying to get at the size of the pulse that's coming out, and then the frequency of the pulse that's going, and then the energy that's associated with that, because everyone's using a different unit in terms of the metrics. And so we're just starting to do that. And we're looking at different kinds of sounds, shipping sounds and gunshot sounds and anything else that can get into the water, and look at the range of things. But that's actually a really good one. So I think we're done. Yeah, they said, thanks.